Welcome to Calculus. It will be my great pleasure to guide you on a journey through a world of calculus during these 24 lectures. The tour begins at our doorsteps and takes us to the stars. Calculus is all around us every day of our lives. When we're driving down a road and we see where we are at every moment and we figure out how fast we're going, that's calculus. When we throw a baseball and see where it lands, that's calculus. When we see the planets and see how they orbit around the sun, calculus. When NASA sends a rocket ship to explore the solar system and they make all these computations about the trajectories and how much fuel to burn in which direction, all of these involve calculus. When we turn on our TVs, calculus. But calculus is not restricted only to physical issues. When we lament the decline in the population of the spotted owl, that's calculus. When we analyze the stock market and we look at economic trends, that's calculus. Calculus comprises a collection of ideas that have had tremendous historical impact. And the reason is that calculus is enormously effective in allowing people to bend nature to human purpose. Much of the scientific description of our world is based on calculus. Descriptions of motion, certainly, of electricity and magnetism, of sound waves or water waves. All of these involve calculus. But in addition to that, calculus is an essential tool for understanding social and biological sciences. It occurs every day when we describe economic trends, when we talk about population growth or decline or medical treatments. All of the description are couched in terms of calculus. That is, its vocabulary, its notation, but more important than any of those are its ideas, its perspectives. So to understand the history of the last 300 years, we certainly must understand calculus. What is it that makes us experience life differently now from the way people understood it and experienced it 300 years ago? Well, most of the difference comes from technological developments. And most of those technological developments are the story of calculus. That is, the implications of calculus that allowed us to develop the technology that changed the way we experience life. It would be extremely difficult to exaggerate the impact of calculus on our life experience. So that brings us to the question of why? Why is calculus so effective? And the answer is that calculus resolves some basic issues associated with change and motion. Just basic everyday motion. If you think about everyday motion, it turns out that idea of just thinking about things moving is a concept that is much trickier than we might at first realize. And in fact, this was pointed out 2,500 years ago. The philosopher Zeno, in 450 BC, proposed several paradoxes about motion. And let me first just say a word or two about what a paradox is. A paradox is an example where you look at some issue from two different points of view. And the two different points of view are both extremely persuasive. And for each one, you say, that's the way to look at that thing. And then you discover that they are in direct opposition to each other. So when you have a paradox, it's pointing the way to a fundamental issue that needs to be resolved. Well, Zeno's paradoxes were paradoxes about motion. And he forced us to confront some questions about basic motion that were not resolved for more than 2,000 years, and they were resolved by calculus. So let me tell you about a couple of Zeno's paradoxes of motion. Two of them involve an arrow in flight. So here was the idea of Zeno's paradox. The first paradox was the following. You have an arrow shooting across the room, zooming across the room. And Zeno asked the following question. He said, okay, we see that the arrow is moving across the room. But let's ask the question, at one instant, is it moving? At one instant, it's in one place. So in what sense is it at that very instant moving? This was a real puzzle. This was a real puzzle about motion. And if you think about it, motion is one of these things that becomes more difficult to understand the more you think about it, because of this, of the nature of Zeno's paradox of the arrow. At every moment, it's not moving. It's in one place. That was a big challenge for people historically, and it was not resolved until calculus. Another example of Zeno's paradox was his paradox called the dichotomy paradox. And this was another paradox involving an arrow, and this time somebody is standing over there and shoots an arrow right at me. And the arrow is coming at me, but if I'm Zeno, I'm very calm. And I'm calm because I think the following thoughts. I say, well, the arrow has to come halfway toward me. And then it has to come half of the remaining distance. And after that, it has to come half of the remaining distance, and so on, half and half and half. And therefore, it has to accomplish infinitely many things, infinitely many traversals of distances. And consequently, it'll never get to me, and I can be perfectly sanguine in my future health by thinking about this paradox. Well, of course, we know in both of these cases that reality is different. That is to say, we know the arrow is moving. We know the arrow will eventually strike its target. So the question is, how can we resolve these issues that Zeno pointed out? Instantaneous motion, and the idea that there have to be infinitely many traversals in order for the arrow to reach its target. Well, when we look at familiar issues, familiar occurrences in new ways, we turn out to find all sorts of fruitful avenues for investigation. And in the case of Zeno's paradoxes led to the calculus, among other things, which have had tremendous impact, as we said, in many areas. Zeno's paradoxes actually bring up issues about infinity, the case of infinitely many traversals before the arrow gets to the target, and the question of infinity about motion. You see, the trouble with motion is that motion really refers to the basic idea that something in motion is at one place at one moment and another place at another moment. Well, when you talk about instantaneous motion, you only have one moment to discuss. So it's a question about dealing with 0 divided by 0. The arrow has gone 0 distance in 0 amount of time. And that issue was a terrific conundrum that was not resolved until, in fact, not only it was resolved by calculus, but it required further elaboration even after calculus was invented to really come to grips with an understanding of that. In fact, that took several hundred years after, or 200 years after calculus was invented, to really pin down that idea. Well, in this course, we're going to emphasize the ideas of calculus, the concepts of calculus, more than the mechanical side of calculus. But I have to tell you that one of the main reasons that calculus has been of such importance during these last 300 years is that it can be used in a mechanical way. It can be used by people who don't really understand calculus. That's part of the power of calculus. And in fact, the word itself, the word calculus, refers to calculating. That is, calculating in this sort of mechanical way. And by mechanical way, what I mean is this. We all learned how to multiply in elementary school, where we took two numbers and we did something and we moved it down and we added things. And, well, most people, when they learn that mechanical way to do multiplication, they're learning a technique, but don't really understand why that technique leads to the answer that they're getting. So it's in the same way that calculus has this calculating mechanical quality to it, that a person can learn the mechanistic strategies by which calculus derives its implications without actually knowing why they work and what's involved in the conceptual background. And I have to tell you that my own students at the University of Texas in my class, when they emerge from my class, they probably have that view of calculus too. Because when you take a calculus class, a lot of the time that you spend in the class is mastering these mechanical methods of doing the actual computations. Well, in this set of lectures, we're going to emphasize the ideas of calculus much more than the mechanical side. And actually, I think it's the mechanical side that gives calculus its reputation for being sort of a fearsome and maybe difficult and forbidding topic. But I have a theory about why calculus is often viewed as a very hard subject. And maybe it's because, and this is just a theory, I may be wrong, but I think it comes from the word. You see, calculus comes from the Greek word calculi, which is the Greek word meaning stones. You see, stones were used for counting things in ancient Greek times. And so, well, stones are hard, you see, and so that's why calculus, well, okay, maybe not. Okay, anyway, but regardless of the reason, calculus certainly does have a reputation for being extremely hard and sort of fierce. And part of the goal of this course is, of course, to make it seem in a totally different light. Calculus can be our friend, you see. But you know, I teach mathematics and I teach calculus, and so I often hear about the fright and the pain associated with mathematics in general or calculus in particular. Like when I'm in an airplane and I sit next to somebody and I divulge that I teach mathematics or teach calculus. Well, they first tend to move away. That's the first thing that happens, and then they're sort of been afraid of it. But one of a particularly delightful example of this representation of the fear and loathing of mathematics and calculus in general came about in Sir Winston Churchill's autobiography, where he was writing about his early life in his autobiography called My Early Life, a Roving Commission. And in chapter 3 of this, he talked about taking examinations, which he had to pass in order to enter the military academy. And he had trouble passing these examinations, which, of course, has always astounded me that Winston Churchill, of all people, would have trouble passing examinations, but that's just the way it was. And so in this chapter 3, he talks about mathematics and how he had to learn mathematics to pass this examination. And so he says the following. He says, "All my life, from time to time, I've had to get up disagreeable subjects at short notice. But I consider my triumph, moral and technical, was in learning mathematics in 6 months." So that was, first of all, pretty good. But anyway, he goes on to describe his recollections of these days. "When I look back upon those care-laden months, their prominent features rise from the abyss of memory. We were arrived in an Alice in Wonderland world at the portals of which stood a quadratic equation." And here's where he gets to calculus. He said, "Further dim chambers, lighted by sullen, sulphurous fires, were reputed to contain a dragon called the differential calculus. But this monster was beyond the bounds appointed by the civil service commissioners who regulated this stage of Pilgrim's heavy journey." That's great. So calculus has this reputation for being a real monster, a dragon with a fiery breath. But anyway, we will attempt to quench these fearsome fires. And by the way, I must say, reading this little excerpt from Churchill, of course, is amazing. Having written 52 volumes of history, he won the Nobel Prize in Literature. So he is delightful to read about Churchill, and particularly this book about his early life. But I think there are other reasons why calculus is viewed as a difficult subject and sort of forbidding. And I have to admit that I think mathematicians will not win the prize for using psychology that calms and soothes the soul. I think we're not going to win that prize. Because I think another reason that calculus is so forbidding is the simple size of calculus textbooks. Now, I've brought a sample here. This is a calculus textbook. And first of all, it does have a lot of benefits, not only mental, but also physical, because people, you learn to heft heavy weights, and so you get strong in that way too. But this is a typical calculus textbook. It has more than 1,300 pages. And of course, to a student, they're very big pages and sort of forbidding, that to a student, these 1,300 pages are all different. But to a professor, it has 2 ideas and 1,298 pages of examples, applications, and variations. And the range and the richness of the implications of those 2 ideas show the power of those 2 insights. And the exploitation of those 2 fundamental ideas lead to this whole world of calculus. And fortunately for us, and for this course, those 2 fundamental concepts of calculus, which are, by the way, called the derivative and the integral, both of those ideas come from everyday observations. Calculus does not require a complicated vocabulary or notation to understand it really authentically. It can be understood in English, and for the most part, we will be talking in this course in English about the ideas of calculus. Okay, so calculus is the study of these 2 basic ideas, the derivative and the integral. Now, we're going to describe them, and we're going to clearly say them in an understandable way in lectures 2 and 3, respectively. Like derivative, lecture 2, integral, lecture 3. And these ideas both will come about by analyzing a very simple situation of a car driving down a straight road and then thinking very clearly about the implication of that idea and how it is that we need to think about such questions as Zeno's paradox of instantaneous motion. What are we going to mean by that? Now let me make absolutely clear that I'm not expecting any viewer of this course to have any sense whatsoever about the meaning of these ideas. In fact, in a way, I sort of hope that the technical terms, derivative and integral, inspire in you maybe something that's foreboding, maybe a sense of impending terror, because that way, when you find out that, in fact, these ideas are accessible and enjoyable, it will be all the sweeter. You see, so this is good. Well, the derivative deals with instantaneous change, how fast things move and change. And the integral gives us a dynamic view of the world, even of the static world. It talks about the accumulation of little things that accumulate into a big thing. And that's what I love about calculus, that it can take it gives us a dynamic view of the world, that even things such as the area of a square or the volume of a cube, all of these things that seem so static can be viewed as growing into the size of the cube or growing into the size of a ball, and looking at that perspective allows us to see the world in a different way. Well, the derivative and the integral turn out to be connected to each other, and they're connected by the fundamental theorem of calculus. And we'll talk about that in lecture 4. Well, and as I said before, both of these ideas arise from a discussion of a car moving down a road, but the same ideas that we get from analyzing this car moving down the road are applicable in these many, many other settings. And that's the strength and the power of mathematics in general and of these 2 ideas, derivative and integral in particular. Now, we're not going to, in this course, we're not going to take the shortcut of oversimplifying. Einstein had a quote on that, went something like, I want things presented to me as simply as possible, but not simpler. And in this course, we're going to present things that are really give you the authentic understanding of the ideas that make up calculus. But the 2 ideas that come from calculus that really make up the foundations of calculus did not appear by magic. The history of calculus spans 2.5 millennia. From the time of Zeno, it was more than 2,000 years that elapsed before calculus became fully developed. And during that time, there was a steady progress of mathematical ideas that needed to be created before we could understand calculus the way we know it now. So I thought that we might take a few minutes here and go through and look at some of the people who participated in this long development and to hear a little about them. So we should actually begin a little bit before Zeno. And in the 6th century, Pythagoras started his famous school of mathematics, and of course he proved the Pythagorean theorem. And then Zeno came along in the middle of the 5th century BC. In the middle of the 4th century BC, there was a Greek mathematician by the name of Eudoxus who developed a method called the method of exhaustion, which was very similar to the integral, one of the basic ideas of calculus. And in fact, we'll see an example of Eudoxus's method in lecture number 9. In about the year 300 BC, Euclid invented the axiomatic method of geometry and wrote maybe the most famous mathematics book ever written, The Elements. In 225 BC, Archimedes used a method of exhaustion to develop formulas for areas and volumes of geometrical figures. And we'll see a great example of that in fact involves his lever in lecture number 9. Well, let's skip ahead a couple of thousand years and get to the year 1600. There were some contributions in between, but it really got going again in the year 1600, when we have Johannes Kepler and Galileo Galilei working on motion, that planetary motion, and describing the motion of objects just in the world, and making mathematical formulas that would describe that motion. In 1629, Pierre de Fermat developed methods for finding maxima of values, and in fact that idea was very close to the idea of the derivative, and we'll see it's applied in our lecture about optimization. So he was very close to being an inventor of calculus, but not quite. In the 1630s, Bonaventura Cavalieri developed a method which he called the method of indivisibles, and we'll see an example of that in a later lecture. René Descartes was famous for his Cartesian coordinate system that made a connection between algebra and geometry. In 1669, Isaac Barrow, who was Newton's teacher, gave up his chair in mathematics for his famous student Newton, and I thought this was such a nice thing to do until I learned that actually he'd gotten a better job and went into a different line of work. But finally, after all this, we come to the two people whose names are most closely associated with the development of calculus, and these are Isaac Newton and Gottfried Wilhelm von Leibniz. These are two people who are most associated with calculus, and we might say they invented calculus or discovered calculus, but actually all of the developments of calculus were definitely incremental. And the fact that both of them independently invented calculus at nearly the same time shows that the ideas were in the air. In fact, Isaac Barrow, Newton's teacher, remember, he actually expressed the fundamental theorem of calculus in some of his lectures, but didn't appreciate the significance of calculus. He wrote it down but didn't appreciate the significance. And it took Newton and Leibniz to really systematize calculus, which was what we come to think of as the core of it. Well, from the time that the calculus was actually invented in the late 17th century, it still took many years for calculus to be really understood. And many people developed the variations on the idea and applied it to many applications in life, from physics, economics, probability, all sorts of things, biology. Johannes and Jacob Bernoulli were two of 8 Bernoullis involved in developing calculus and applying it in Europe. Leonhard Euler developed a tremendous amount of mathematics, including many applications and extensions of calculus, especially infinite series. Joseph Louis Lagrange worked on the calculus of variations. Pierre-Simon de Laplace worked on partial differential equations and applied calculus to probability theory. Jean-Baptiste Joseph Fourier invented ways to approximate certain kinds of dependencies, certain kinds of descriptions of things in terms of what are called circular functions like sines and cosines. And by the way, this idea of taking a path, such as the path of a planet, and describing it by a collection of circles really came from the old idea of using epicycles to try to describe the elliptical orbits of planets. So by adding a lot of these circular motions, you can approximate other kinds of curves. Augustin Louis Cauchy developed ideas about infinite series and tried to formalize the idea of limit. We'll find that the idea of a limit comes up in both the derivative and integral, and it is one of the challenges to calculus that neither Newton nor Leibniz really were able to master. And it took another 180 years before people really could pin down that idea of limit, which is when numbers are converging toward one number. But we'll talk about that much more in future lectures. In the 1800s, George Friedrich Bernhard Riemann developed the modern definition of the integral, which is one of those two ideas of calculus. And in the middle of the 1850s, Karl Weierstrass formulated, finally, the rigorous definition of limit that occurs in this calculus book and that we use today. And then notice again that this 1850 is 185 years since Newton first developed calculus in 1665. So it took a long time to understand calculus, even after it was invented. So if you don't understand calculus the first time you see it, you can take some solace in the fact that it took humanity 2,000 years to develop it, and it took even after it was developed, it took several hundred years to understand it. It takes everybody a long time to understand it, and in fact, essentially nobody understands calculus the first time they take it. I didn't understand calculus the first time I took it, and among my friends who teach mathematics, they didn't understand calculus the first time they took it, almost everybody. In fact, for most of us who teach calculus, the time we understood calculus was the time we taught it, and I recommend this as a method for learning anything. Well, this then gives a sense of the history of calculus. And I'd like to take the remaining part of this lecture to just tell you the structure of the upcoming lectures, the structure of the course. So we'll begin in lectures 2, 3, and 4 comprise a collection of lectures that really present the fundamental ideas of calculus. In lecture 2, we introduce the idea of the derivative and say what the definition is and what it means. And then in lecture 3, we do the same thing to the integral. We'll say what the definition of the integral is, how it comes about. And then in lecture 4, we introduce the fundamental theorem of calculus, which connects the two. And if I have done my job correctly, you will find that lecture 4 is sort of a letdown in that it's obvious that the derivative and the integral are two sides of the same coin, that they're related to each other. But that was an insight that took some time historically to clarify. Well, after we get through lecture 4, then we proceed to investigate each of these fundamental ideas in more detail. The next lectures are a sequence of lectures about the derivative. And in the collection of lectures about the derivative, we're going to look at the derivative and see that, in fact, although we had presented the idea of the derivative in terms of motion, of a car moving on a straight line, we'll see that same abstract procedure that's the derivative actually also tells us other things. It tells us about, it can be interpreted in terms of graphs of functions, which we'll talk about and introduce in later lectures. But it says that the same procedure that tells us the instantaneous velocity of a car also tells us the slope of a tangent line of a curve. And that kind of connection is an interesting one that gives the power to the ideas of the derivative. Similarly, we're going to take the derivative and look at it from the point of view of its algebraic manifestations. One of the properties that makes the derivative so potent and the integral is that you can do it algebraically, and that's this mechanical side that students view as most common. The part that they deal with most is learning how to manipulate the algebra. So we'll see the derivative then physically, that is with the car moving, and then graphically, and then algebraically, and then we'll see it applied to different application areas, such as volumes, formulas for the volumes of objects. All of these things have manifestations about the derivative. After that, we turn to the integral, and we have a similar sequence of lectures that present the integral in those terms. That is to say, graphically, algebraically, and in terms of their applications to many different areas. So by taking these fundamental ideas and viewing them in different ways, then that will show the richness of these themes. Then the last half of the course will demonstrate the richness of these two ideas by showing lots of examples of their extensions, their variations, and their applications. Well, the purpose of these lectures is to explain clearly the concepts of calculus and to convince you that calculus can be understood from simple scenarios. Calculus is so effective because it deals with change and motion, and it allows us to view our world as a dynamic rather than just a static place. Calculus provides a tool for measuring change, whether it's change in position, change in temperature, change in demand, or change in population. But in addition to that, I like to think that calculus is intrinsically intriguing and beautiful, as well as just being merely important. So calculus is a crowning intellectual achievement of humanity that all intelligent people can appreciate, enjoy, and understand. I look forward to exploring calculus with you during the next 23 lectures. Bye for now.